Welcome to the deep dive. Today, we're diving into a really interesting area of AI, and one that's moving super fast. The safety of large vision language models, or LVLMs for short. They're basically like ChatGPT, but with a whole other level of complexity, because they can understand and generate both text and images. Our deep dive today is going to be based on excerpts from a 2025 research paper. It's called A Survey of Safety on Large Vision Language Models: Attacks, Defenses, and Evaluations.
Quite a mouthful.
Yeah. But it's packed with insights about why this all matters to you, especially as these LVLMs are showing up everywhere, from self-driving cars to healthcare.
It really is fascinating to see how this field is bringing together the power of language models with AI's ability to process images. I mean, just imagine a world where AI can not only understand what you type, but also what you see in an image.
Yeah, that's mind-blowing.
It opens up so many possibilities. Like AI could create super detailed descriptions of images, answer really complex questions about visual scenes, and even help doctors with medical diagnoses by analyzing scans.
That sounds incredible, like something straight out of science fiction. But I guess like any powerful technology, there's always the flip side, the potential for misuse or even harm. The researchers in this paper actually found that LVLMs, while they're capable of amazing things, are also uniquely vulnerable. So what makes them so susceptible to attacks?
Well, there are two main reasons. The first is what the researchers call visual input expansion. Basically, by adding images to the mix, you're creating a whole new attack surface. Unlike text, which is made up of separate words and characters, images are continuous and incredibly complex. Think high dimensional.
Right, so it's way harder to control for every single detail.
Exactly. It's much easier to subtly tweak a few pixels in an image than it is to sneak malicious code into a sentence. Those tiny, almost invisible changes can completely mislead the model.
So it's like finding a secret backdoor that's almost impossible to guard.
Pretty much.
Okay, so that's one vulnerability. What's the second?
The second one is something called safety degradation during fine-tuning. And this might sound counterintuitive.
I don't know.
The process of making these LVLMs really good at specific tasks can actually make them less safe overall.
Wait, really? I would have thought more training means more safety.
You'd think so, right? But
No.
it's not that simple. You see, as these models learn new things, they can sometimes forget some of their original safety training. It's called catastrophic forgetting, and it's a big headache for developers.
Oh, wow, I see the problem.
Think of it this way. Let's say you have an LVLM that's been fine-tuned to write marketing copy. It might be amazing at that, but because it's forgotten some of its safety protocols, it could be tricked into generating something harmful.
So it's like a trade-off almost.
In a way, yeah.
Okay, so we have these vulnerabilities. How do those vulnerabilities actually get exploited? The paper talks about different levels of access that attackers might have. Can you walk us through those?
Absolutely. The researchers break it down into three categories: white box, gray box, and black box. White box is the scariest scenario. It's like the attacker has a complete blueprint of the model. They know all its inner workings, its parameters, even the exact data it was trained on.
So basically they have all the keys to the kingdom.
Exactly. And they can use that knowledge to craft really precise and effective attacks.
Yikes. All right, what about gray box attacks then?
Gray box is kind of in the middle. These attackers have some knowledge about the model. Maybe they know the type of architecture it uses, but not the specific details.
So they have a general idea, but not the full picture.
Yeah, like they might have a floor plan of a house, but they don't know the exact placement of every room or piece of furniture.
Okay, so still dangerous, but less precise.
Right.
And then finally, we have black box attacks. It sounds like these are the trickiest for attackers.
In some ways, yes. Black box attackers have the least amount of information. They can only interact with the model by giving it inputs and seeing what outputs it spits out.
So it's like trying to figure out how a machine works just by pressing buttons and seeing what happens.
That's a good way to put it. But even with limited knowledge, clever attackers can still find ways to manipulate the model.
So even without knowing the model's blueprint, they can still find cracks in the armor. Okay, so now we've got a handle on these different levels of access. What kinds of attacks are actually happening out there in the wild?
The researchers talk about two main categories: inference phase attacks and training phase attacks. Inference phase attacks happen when the model is actually being used. The attacker is trying to trick it into producing something unsafe.
Can you give us some concrete examples?
Sure. So one example of a white box attack is something called adversarial image prefixes. This is where an attacker subtly manipulates the image, like adding a tiny imperceptible pattern. This can cause the model to completely misinterpret what it's seeing.
That is sneaky. How about gray box attacks during inference?
One example there is transferring adversarial examples. Let's say an attacker has access to a model that's similar to the one they want to target. They can craft an attack that works on that similar model and then try to transfer it to the target model, hoping it'll exploit similar vulnerabilities.
So they're basically trying to find a skeleton key that can open multiple locks. Clever, but devious. All right, and what about those black box attacks during inference? How do those work with such limited information?
Well, those often rely on something called prompt engineering. The attacker might try to embed malicious instructions within the image itself, like hiding commands within the typography. The model might process the image and follow those hidden instructions without realizing it's being manipulated.
So even seemingly harmless images can actually carry hidden dangers.
That's right.
We've talked about inference phase attacks, but you also mentioned training phase attacks. How are those different?
Training phase attacks are even more insidious because they involve messing with the data that's used to train the model in the first place.
So it's like poisoning the well at the source.
Really good analogy.
Can you give us some examples of what those look like?
Sure. One method is label poisoning, where attackers intentionally mislabel data during the training process. Imagine you have a data set of images meant to teach a model to recognize different political figures. An attacker could subtly alter the labels, so the model learns to misidentify those figures.
And that could lead to all sorts of problems down the line, like misinformation or bias.
Absolutely.
Is there another type of training phase attack?
Another sneaky one is backdoor trigger attacks. In this case, attackers hide specific triggers within the training data. These triggers could be anything, really. A specific pixel pattern, a hidden word or phrase. When the model encounters that trigger later on, it activates a pre-programmed malicious behavior.
So it's like planting a landmine that sits dormant until someone steps on it.
That's a pretty good way to visualize it.
Attackers are getting pretty creative.
They are.
But I'm guessing the good guys aren't just sitting back and letting this happen.
Definitely not. Researchers are working hard to develop equally creative defenses. Just like the attacks, these defenses can be categorized based on when they target the model, during training or during use.
Okay, so are we about to jump into the world of LVLM defense mechanisms? Because this is getting really interesting. But let's pause here for a moment. We've covered a lot of ground. The unique vulnerabilities of LVLMs and how those vulnerabilities can be exploited through various attacks. But stay tuned, because after a quick break, we'll delve into the fascinating world of how researchers are fighting back and developing ways to protect these powerful models from those who seek to misuse them.
Yes, we'll be back to explore all the strategies and techniques that are being used to make these models more resilient and secure.
All right, so we're back and ready to dive into the world of defenses against those LVLM attacks we talked about. It's like a technological arms race, isn't it?
It really is. But the good news is researchers are coming up with some pretty innovative ways to protect these models, both during their initial training and while they're being used out in the wild.
Okay, so let's start with those defenses during training. If those training phase attacks are like poisoning the well, how do you make sure the water stays clean, so to speak?
Well, you can think of it like this. You're trying to build the model with safety baked in from the ground up. It's not just about reacting to attacks. It's about proactively making the model more resistant to being manipulated in the first place. One way researchers do this is through what they call data-driven refinement.
So they're basically being super picky about what the model learns from.
Exactly. Remember how we talked about poison data? Well, data-driven refinement is all about making sure the training data is squeaky clean. They filter out any potentially harmful examples, and they even include data that specifically teaches the model how to handle adversarial inputs.
It's like giving the model a healthy diet so it grows up strong and can resist those bad influences.
That's a good way to put it.
What other strategies do they use during training?
Another really cool approach is called strategy-driven optimization. This is where they develop special training techniques to enhance safety, but without sacrificing the model's overall performance.
So they don't want to make it too safe that it becomes useless.
Right. It's a balancing act.
Can you give us an example?
Sure. So one technique they might use is called robust training. This strengthens the model's visual encoder, which is the part that processes the images. It basically helps the model become less susceptible to those tiny pixel-level manipulations we talked about.
Oh, right. So it's like teaching the model to ignore those little visual distractions.
Exactly. It's like giving it a mental workout specifically for safety.
Okay, so we've talked about defenses during training, but what about protecting the model once it's out there being used?
That's where inference phase defenses come in. These act like a shield, protecting the model in real time as it's processing information.
So if training phase defenses are like building a fortress,
Yeah.
these are like having guards on patrol.
Love the analogy.
And just like a good security system. These defenses work at different levels. One that the paper mentions is input sanitization.
Ah, yes. Input sanitization.
So this is about cleaning up any potentially harmful stuff before it even reaches the model.
Exactly. Think of it like a bouncer at a club, checking IDs and making sure no troublemakers get in.
Right, keeping the riffraff out.
They might filter out weird noise in images or rewrite prompts to make sure they activate the model's safety features.
So it's all about catching those sneaky manipulations before they can do any damage.
That's the idea.
Are there other layers to this security system?
Absolutely. Another important layer is internal optimization. This focuses on making the model itself more resilient to attacks.
Okay, so how do they actually do that? How do you make a model more resilient?
Well, one technique is called logic biasing. It's a bit technical, but essentially,
Go on.
you're subtly nudging the model's decision-making process towards safer responses, even if it gets some weird or tricky inputs.
So you're kind of rigging the game in favor of safety.
You could say that.
Are there any other ways to optimize the model internally?
Researchers are also working on correcting for what they call visual-induced misalignment. Basically, they want to make sure that the model's understanding of images aligns with its understanding of text. When these two things clash, it can create vulnerabilities that attackers can exploit.
So it's like making sure the model isn't getting mixed messages.
Exactly.
What other defenses do they use during inference?
Another critical one is output validation. This acts like a final checkpoint before the model's output is released to the world.
So it's like a last chance to catch any potentially harmful stuff.
Precisely. These defenses might scan the output for certain keywords or phrases that are considered unsafe,
Yeah.
or even rewrite the output to make it safer.
It's like having a safety net to catch any slip-ups.
A very good analogy.
Are there any other types of inference phase defenses?
One more worth mentioning is multi-stage integration. This involves combining techniques from all those layers we talked about to create a kind of super defense strategy.
So it's like recognizing that no single defense is perfect. So you need multiple layers of protection.
Exactly. It's like a castle with high walls, watchful guards, and a secure inner sanctum.
So you're making it as hard as possible for the attackers to break in.
That's the goal.
All these defense mechanisms sound super sophisticated. But how do researchers know if they're actually working? How do they actually test the safety of these LVLMs?
That's a great question. And it leads us into the world of LVLM evaluation. It's a pretty complex area.
I bet.
But essentially, researchers have developed a whole bunch of different methods and benchmarks to assess how safe and robust these models are.
So it's not just a simple pass or fail test.
No, definitely not. There are lots of challenges when it comes to measuring the safety of LVLMs.
Like what?
Well, one of the biggest challenges is just figuring out how to set up the evaluation in the first place.
Okay, so how do they do it?
There are a few different approaches, each with its own pros and cons. One basic approach is called rule-based matching, where they scan the model's outputs for specific keywords or phrases that are known to be unsafe.
So it's kind of like a list of banned words.
Yeah, you can think of it that way.
It's simple, but I guess it can miss things.
It doesn't really take context into account, so it can miss more subtle forms of harmful content.
You need something more sophisticated.
Right.
What else do they use?
Another approach is human-assisted evaluation. This is where actual humans review the model's outputs and judge how safe they are.
Okay, so that sounds more accurate.
It is, but it's also really time-consuming and expensive. And you also have the issue of subjectivity.
Right. Different people might have different ideas about what's safe or not.
Exactly.
So what's the solution?
Well, researchers are also exploring what they call fine-tuned model-based assessment. This is where they train a separate model to evaluate the safety of the LVLM's outputs.
So it's like AI judging AI.
Kinda, yeah.
Interesting.
This approach can be pretty effective, especially when you combine it with human oversight.
So you're using AI to do the heavy lifting, but still having humans double check to make sure things are on track.
That's right.
Are there any other methods they use?
Yes. One more that's getting quite popular is GPT proxy-based assessment. This uses a really powerful language model like GPT-4 to evaluate the LVLM's responses.
Wow, so it's like having a super intelligent AI judge another AI.
It is a bit mind-bending.
It is.
But the idea is that GPT-4 is so good at understanding language and context that it can provide really valuable insights into the nuances of the LVLM's outputs.
I see.
Of course, it's not perfect because GPT-4 has its own biases and limitations.
Right. We're still ultimately relying on AI to judge AI.
True.
Okay. So we have all these different ways to set up a safety evaluation. But what are the actual things they're measuring? What are the metrics they look for?
Well, there are quite a few different metrics, each designed to capture a different aspect of safety.
Like what? Give us some examples.
One of the most straightforward ones is the attack success rate, or ASR. This basically measures how often an attacker is able to successfully trick the model into producing a harmful output.
So the lower the ASR, the better.
Exactly.
What else?
Then there's the Safety Risk Index, or SRI. This goes a step further and tries to measure how severe the harmful outputs are.
So it's not just about whether the model generates bad stuff. It's about how bad that stuff actually is.
Precisely.
Makes sense.
There's also the Attack Success Degree, or ASD, which measures how aware the model is of its own harmful behavior.
So, like, is it intentionally being bad?
In a way, yes.
Fascinating.
Then there's the Perfect Answer Rate, or PAR, which measures how often the model gives a perfectly safe and appropriate response.
So basically, how often it does exactly what you want it to do.
That's it.
And finally,
There's the Refusal Rate, or RNAR, which measures how often the model correctly identifies a harmful query and refuses to answer it.
it's like it's saying, nope, I'm not going there.
Exactly.
I'm starting to realize just how complex this whole evaluation process is.
It is.
Are there any kind of standardized tests that bring all these metrics together?
Yes, there are. The paper highlights a bunch of different benchmarks that researchers have developed. These can be broadly categorized into two types: strategy effectivity benchmarks and safety capability benchmarks.
Okay, break those down for us. What?
So strategy effectivity benchmarks are all about testing the effectiveness of different attack and defense strategies. It's like a controlled environment where researchers can pit these techniques against each other and see what works best.
So it's kind of like a battleground for AI safety?
You could say that.
And what about those safety capability benchmarks?
Those are more general purpose. They're designed to evaluate the overall security of the model. They usually include a bunch of different tasks and scenarios that are designed to challenge the model's safety mechanisms.
So it's like a comprehensive safety inspection.
Exactly.
Are there any specific benchmarks that are particularly important?
Yes, there are a few that stand out. One is called How Many Unicorns?
That's a strange name.
It is.
Yeah.
But it focuses on a specific type of attack called an out-of-distribution, or OD attack.
Okay, what's an ode attack?
It's basically where you give the model inputs that are completely different from the data it was trained on.
Yeah.
You're trying to see how well it can handle unexpected situations.
So it's like testing the model's street smarts.
Yeah, you could say that.
Are there other benchmarks we should know about?
Another important one is called Safety Bench, which stands for Multimodal Safety Benchmark. This one is specifically designed for LVLMs, and it tests their safety against attacks that target both the visual and textual modalities.
So it's like a real stress test for the model safety systems.
Exactly. The Safety Bench includes all sorts of scenarios, like identifying illegal activities, detecting hate speech, and resisting attempts to make the model generate malware. Well, the findings have been pretty interesting. They've shown that even LVLMs that are specifically trained for safety can still be vulnerable to these types of attacks.
So it's a constant battle.
It is.
Is there one more benchmark you want to mention?
Yes. One more that's worth highlighting is called SIUO, which stands for Safe Input, Unsafe Output.
That one's pretty self-explanatory.
It is.
So you're testing whether the model can handle situations
Yes.
where the input is perfectly fine,
Yeah.
but the model's own knowledge or biases might lead it to produce a harmful output.
That's exactly right. And it's a really tricky type of safety violation to catch and prevent.
I bet.
The SIUO benchmark has actually shown that even some of the most advanced LVLMs out there struggle with these scenarios.
Wow, so even the best models aren't perfect.
Not yet.
Okay, we've talked a lot about these benchmarks and evaluations. It's clear that researchers are putting in a lot of effort to make sure these LVLMs are as safe as possible. But have they actually tested any specific LVLMs using these methods?
Yes, they have. The paper actually talks about some evaluations they did on a new LVLM called Deepseek Janus-Pro.
Deepseek Janus-Pro, that's a cool name. What's so special about this one?
Well, Deepseek Janus-Pro is one of the latest and greatest LVLMs. It can understand images and generate images. It's actually one of the first models to be able to do both of those things really well.
That's impressive. But how did it do in the safety tests?
That's where things get a little interesting. Despite being so advanced in other areas, Janus-Pro actually seems to struggle with safety.
Really? That's kind of surprising.
Yeah, you would think that a model this sophisticated would have safety baked in. But when they ran it through the SIUO and safety bench evaluations, it revealed some pretty significant weaknesses.
Say, I'm all ears. What do those benchmarks show?
Well, on the SIUO benchmark, Janus-Pro didn't do so well on open-ended questions related to safety.
Can you give us an example?
Sure, imagine you ask it something like, what are the dangers of mixing bleach and ammonia? It might give you a wrong answer, or even a dangerous answer.
Yikes. Not good. And what about the safety bench? How did it perform there?
On that benchmark, Janus-Pro struggled with scenarios involving illegal activities or violence. It was much more likely to produce harmful outputs in those situations, even when the input itself wasn't that bad.
So it seems like Janus-Pro, while super powerful, still needs some work when it comes to safety.
Yeah, that's a good way to put it.
It's a good reminder that even the most advanced AI systems can still have these vulnerabilities. It's like a never-ending challenge. This whole deep dive has been incredibly eye-opening. I feel like I've learned so much about this crazy world of LVLMs, the amazing things they can do, but also the very real threats they face. And it seems like researchers are in this constant race to develop effective defenses against those threats.
You got it. It's a fascinating field that's constantly evolving. I can't wait to see what the future holds.
Me too. But before we wrap things up, I want to leave our listeners with something to ponder. The paper mentioned that black box attacks are becoming more and more common.
Yes, they are.
And they're particularly worrying because they're so hard to defend against.
Right.
What's really interesting is that these attacks are actually using the model's own capabilities to get around the defenses.
That's right.
So this makes me wonder, could we be headed for some kind of AI arms race where the attackers and the defenders are constantly trying to outsmart each other?
That's a great question, and it's something that researchers are really thinking about right now. It's definitely possible that as LVLMs get more powerful, the attacks against them will also get more sophisticated. It's a continuous cycle of innovation and adaptation.
Kind of like a never-ending game of cat and mouse.
Exactly.
And I think this highlights how important it is to have a really proactive and comprehensive approach to LVLM safety.
Absolutely.
We can't just wait for attacks to happen and then try to react. We need to be thinking about security from the very beginning, from the design and training of these models, all the way to how they're used in the real world.
I agree.
This deep dive has really given us a lot to chew on. But before we go, I want to point our listeners to a resource that was mentioned in the paper. It's called the Awesome LVLM Safety Repository on GitHub. It's a fantastic place to stay updated on all the latest research in this field.
Yes, it's a great resource.
And I think it's important to remember that understanding the security of AI systems like LVLMs is becoming more and more important for everyone, not just the experts. As these technologies become more and more part of our lives, we all need to have a basic understanding of the risks involved.
Absolutely. We all have a role to play in making sure these powerful technologies are used responsibly and ethically.
Well said. This deep dive has been truly enlightening, and I encourage all our listeners to continue learning about LVLM safety. Stay tuned for the final part of our deep dive, where we'll wrap up our discussion and explore some potential future directions for this fascinating field. And we're back for the final part of our deep dive into this whole world of LVLM safety. We've covered so much the vulnerabilities of these models, all the crazy attack and defense strategies, and even how researchers are trying to measure and benchmark security. But before we wrap up, I wanted to touch on one more thing that I think is really important, the future of this whole field. So where do you see things going from here? What kind of trends or challenges do you think are on the horizon?
That's a great question. I think as these LVLMs become even more powerful and integrated into our lives, we're going to see the challenges evolve as well. One thing that's already happening is the rise of those black box attacks we talked about. Remember how we said those are the trickiest to defend against?
Yeah, because attackers don't need to know all the model's secrets.
Right. And they're getting more and more creative in how they exploit the model's own abilities to bypass defenses.
It's kind of scary. Like, we're entering this era where it's a constant battle between attackers and defenders.
It's definitely a bit of a chess match. Both sides are trying to outmaneuver each other.
So how do we even keep up?
Well, I think it requires a very proactive approach to LVLM safety. We can't just sit back and wait for the next attack. We need to anticipate what might be coming and develop defenses that can adapt.
It's not just about building stronger walls. It's about predicting how they might try to break in.
That's a great way to put it. And this is going to require a lot of collaboration between researchers, developers, policymakers, everyone really.
It sounds like a pretty massive undertaking.
It is, but I think there are a few key areas where we can really focus our efforts. One is to keep pushing the boundaries of those defense mechanisms we talked about. We need to come up with even more robust and adaptable ways to protect these models.
So defenses that can learn and evolve as the threats change.
Exactly. Another really important area is to develop even better benchmarks and evaluation tools. Remember those benchmarks we discussed?
Yeah.
We need more of those, and we need to keep refining them so that we can accurately measure how safe these models really are.
So we can really put them to the test.
Exactly. And finally, I think we need to have some serious conversations about the ethical side of all this. As these LVLMs become more powerful, we need to think about how they could be misused or abused. We need to establish clear guidelines for responsible development and use.
It's not just about making them safe from hackers.
Yeah.
It's about making sure they're used for good.
Exactly.
This whole deep dive has really been a wild ride. I've learned so much. And it's made me realize just how complex and important this whole area of LVLM safety is.
It is a really fascinating field, and it's changing so quickly.
I'm a little nervous about what the future holds, but also excited to see what new developments come out of all this research.
Me too. I think if we stay focused on these challenges and keep pushing the boundaries of what's possible, we can harness the power of LVLMs for good.
I like that positive outlook.
Yeah.
Before we sign off, I want to thank you again for being here and sharing your insights.
It was my pleasure.
And to all our listeners out there, keep exploring, keep learning, and stay engaged in these important conversations. Remember that awesome LVLM safety repository we mentioned. That's a great place to stay up to date on everything that's happening in this field. The more we all understand about AI safety, the better equipped we'll be to navigate the future. That's it for this deep dive. Thanks for joining us. And until next time, stay curious.